All right, thank you. So I want to discuss some of the things we have been doing in the last 5-10 years or so. And the topic will be slightly different from what we have heard. So everything we heard so far was connecting physics and information theory. So let me add one more element, physics. Let me add statistics. And in many ways, what we have heard so far is something going in this direction. Right, so how we can use some of the concept of information theory in statistics and statistics for physics. And this is, of course, a very good thing. I mean, there are a lot of activity in this direction. And somehow what I want to discuss is the other direction. Right? I want to go from physics to information theory and from physics to statistics. And by that, what I mean is that what I would really like to do is to solve some problems which are arising in statistics or in information theory using some tools from physics. Okay? And obviously, these two are related. Actually, these are essentially the same thing from my point of view. All right, so this is the idea, and I will try to build up more and more complex stuff well, in lecture 2 and lecture 3. But the first lecture, I will try to basically stay at a very, well, not low actually, but introductory level. Okay, so if I'm too slow, just tell it to me. If I'm too fast, tell it to me. And don't let me talk. I like to talk, but I like to be interrupted. All right, so what I want to do in this 1 hour and a half or so is to discuss a few examples. And everything will be based on the point of view of statistics. And to be more precise, statistical inference. All right, what is statistical inference? It's what physicists call inverse problem. And instead of giving a definition, I will move directly to an example. So let's give the first example. And my first example will be something which we can call classical statistics. And actually, it's coming from the book of McKay called Information Theory, which you should read because it's great. I have seen a copy somewhere yesterday. Someone was reading it. Oh, great book. All right, so this is my example. Imagine the following situation. We have a source of radioactive particles here. So this is emitting particle in this direction. So let's call this direction Y. Okay? And so particles are emitted. And at some point, they are, I don't know, there is something happening. So for instance, let's say that this is like a positronium. So it decays, and there is a flash of photon, and you can detect it. Okay, so it emitted, boom, here you detect it here. Now we build a machine to see where the particle has emitted the flash of photon, right? So where the particle has done its decay. And of course, we would like to build a machine which is able to see as many events as possible. This is what we do in physics. But, I mean, life is hard, and we don't have an infinite amount of money, so we do what we can. And let's assume that we have built a machine which is doing the following job. If the radioactive decay happens between 1 centimeter and 20 centimeters, and you can replace centimeter by your favorite unit, inches or whatever, we can observe it. Right? So particle is emitted. If it decays here, we observe it. If it decays here, we don't. If it decays here, we don't. Right? So we see all the decays that arise here. And so that's it. We launch the experiment. And after a while, we are collecting the data because we are doing physics. This is what we do. And this is what we see. We see that there have been one decay at this distance, one here, one here, one here, one here, one here, one here. All right? Well, these are the data, and now we want to know what is the characteristic length scale lambda. Right? We know the law of radioactivity. I mean, it's a simple process. We know that essentially what should happen is that a particle, given a characteristic distance lambda, the probability that it decay at position y is 1 divided by lambda exponential minus y over lambda. Okay, that we know from physics. And the problem of statistical inference is saying, okay, so these are the data. How do we find lambda? It's actually not such a simple problem, but okay, it has been solved for us. And the first thing you want to do is to ask yourself, okay, given lambda, what is the probability to observe an event here, an event here, an event there? Now, this is not given by this law, because this is telling us probability that there is a decay at position y. This is not the same as the probability to observe it, because obviously, since I built a machine, or a detector if you want, between 1 and 20 centimeters, any event here or any event there, I don't see them. Right? So first of all, what we need to write is the probability to observe an event. Okay, let's call it P observation. Right, if y is larger than 1 and smaller than 20, well, we should observe something like this. Otherwise, the probability is 0. Otherwise. Okay, but we also want probability to be normalized. So maybe I should add a little z here to normalize this. We can compute the normalization. It should be exponential minus, well, I don't want to do the computation now, so. Okay, so you can normalize z, and it is equal to exponential minus 1 over lambda. All right, so now this is the probability to observe an event somewhere, given that the truth is lambda. What we are looking for is the true value of lambda. Okay? Now, of course, we know also from physics that the probability to observe something here for the first particle is totally decorrelated with the probability to observe it for the second particle. These are uncorrelated events. So the probability to observe a collection the collection of value y is just given by the product. Right, so now we ask, what is the probability to have observed this particular set of events? So y is going from 1 to 1, 2, 3, 4, 5, 6, so my n is 7 if you want. And this is just given by the product of these probabilities. N, okay. All right. So this is interesting. This is telling us basically what is the probability to observe a given solution, so or if you want a given set of events, given the truth. Now, this is not exactly what we want to know because we don't care too much about this probability. We care about finding lambda. Now, there is a way to inverse this relation, and it's something that has been done for us by essentially people who invented statistics. So Laplace in France, Gauss in Germany, and then the hero of statistics is Fischer in Britain. And one of the ways to understand this is to approach it with some more probabilistic point of view, which is what physicists are happy to do most of the time, is to think about lambda as a random variable, and to think, okay, lambda is like a random variable, and let's try to have a distribution on it. And this is typically the Bayesian point of view. And you might complain about it, and people complain about it because they said, no, lambda is not a random variable, it's the truth, it is a number. Maybe this particle has a typical length of 17 centimeters, so I should not think about this as a random variable. Yet, it is useful to think about quantities like this as random variable, and this is what Bayesians do, and the probability express our uncertainty about it, right? It's like when you are saying, will it be raining tomorrow? And you say, well, yeah, 50-50. You are treating something which is not random, that is the weather tomorrow, it will be ever raining or not, as a random variable, because you are saying, well, you know, it's 50% to rain, 50% not to rain. So you are treating probabilities as uncertainties. So this is useful to do this, and if you do that, actually, this thing here become a conditional probability. It's the probability to observe y given lambda as a particular value. Now it sounds like I have done much here, but basically I have solved the problem, because now I can just use standard probability techniques. And okay, let me try to think about what to do. I will use it here. Okay, and I will write what is known as the Bayes theorem, even though it's kind of a triviality, but it's actually one of these triviality that turns out to be deep. All right, so now I wrote a sample identity, which is known as a Bayes identity. If you want to prove it, you just send this thing on this side. You realize this is a joint probability of lambda and y. This product is also the joint probability of lambda and y. So it has to be true, because P of A given B times P of B is equal to P of A and B. All right? And now I need to give some names to this thing. This is called the likelihood of lambda given the data. So I insist, this is not a probability distribution over lambda, it's a probability distribution over the y. So if I think about this, when I plug the data in it as a function over lambda, I can do this. It is, after all, a function that depends on lambda. It's not a probability distribution. Okay? It's called the likelihood. Right, so this guy here is likelihood. Now this guy is called the prior, and this is called the evidence. But most of the time we will actually not even use this. And since we like physics, I'm sorry? Oh, good. I will just call that big Z and just say this is a normalization. And it turns out it will be exactly the same as the partition sum. Okay, and now this thing on this side is called the posterior. So what it means is the following. The probability distribution over lambda given the data, which is what I really want to know. I want to know what is the probability that lambda is a given value. And ideally, that will be something peaked very much about one given value, is given by the product of the likelihood, which is the probability to have generated this value given that lambda was the truth, times something which is called the prior. And the prior means that it should contain the information I have a priori on lambda before the experiment. Okay? And here I have a normalization factor because every probability should be normalized. So what to choose here? Because this is said by physics, and this part here, well, I said something like, well, it should say what we know about the problem before. It is actually something that people have argued and complained and loved or hate for about 1 or 2 centuries now. And there is still a lot of discussion about what to do here. Okay? So I will not go into these discussions because I will be cheating a bit. For classical statistics, you will see that it doesn't matter too much. Well, it does actually, but at least for the example I will give, it doesn't matter. And for what I will do in the following, I will set the problem such that the prior is perfectly well defined. Still, let's try to solve this problem, and let's follow what McKay is doing in his book. One thing you might say is, well, I don't know anything about lambda a priori. Okay, I don't know anything about it. So I should use a flat probability distribution, totally uniform between all values of lambda, between 0 and plus infinity. And this is what people do. And of course, it's a bit of a problem because there is no such thing. There is not a probability distribution between 0 and infinity because it's not normalizable. I mean, it doesn't exist. It's true, and there are ways how to deal with this. Point is, we are physicists, we don't care about infinities as long as everything is finite at the end. So if I rewrite this like that, this is a constant. Maybe it's infinity, maybe not. But I'm divided by a normalization. So, by a change of notation, I'm absorbing everything into normalization, and it should not be a problem. Okay? So if we assume a uniform prior, okay, we are doing something which is a bit fishy. But we arrive to this relation. In that case, the posterior probability is essentially proportional to the likelihood. Okay? So now we are ready to solve the problem. It's natural to say, fine, let me actually, before solving it, making a plot. So how does it look, this likelihood? Let me plot it in function of lambda. So if you have data that look like that, it's a function that essentially look like this. There is a max around 10, because that's what I use to generate the data. And so this is telling you somehow a degree of belief of where should be the truth for lambda. Now, if you have more observation, what you will see is that this thing will start to peak, and you will have a nice little Gaussian with very small variances around the truth. Okay? But since I have only 7 observations, I still have something like that. Now, what is the natural guess that we should do? Well, we should probably take the maximum, right? In this, after all, the most probable. So in statistics, people like to call, and in information theory as well, as a matter of fact, every guess you make on an unknown is called an estimator, and is denoted hat. So lambda hat, ML, so that stands for maximum likelihood. Maximum likelihood is essentially what you have done here. When you assume uniform prior, you maximize the posterior, which is the same as maximizing the likelihood. Okay, you define it as the argmax of 1 over the number of observation of the log likelihood. P of y given lambda. Right, because of course, maximizing a function or maximizing the log of a function is the same thing. All right, that's basically the end of the first example. And this is, I mean, it's not totally true, but this is basically anything you need to know about inverse problem in the classical setting. It's not true, as a matter of fact. Much more, it isn't, you know. There are a lot of very interesting stuff, especially in the choice of prior you can do. But it's fair to say that maximum likelihood is kind of the king of the castle here, and that everyone is using it. So does it work? And that's the first thing you need to ask, right? There are some fishy things that I did here. And in fact, when it was derived, well, again, you know, historian could disagree on who derived it first. I mean, maybe Laplace, maybe Gauss, but it's Fischer who gave the name maximum likelihood to this method. Certainly, Fischer did not use this method. I mean, he disliked heavily all this Bayesian nonsense, as he said. And the way he thought about it is, this is my method. Okay, by the way, it's a function of the data. Let me prove to you that it works. And by proving that it works, what I want to say is, imagine I'm making a huge number of observations here. So I'm letting n going to infinity. So I'm still observing only events between 1 and 20, but I'm not observing only 7 events. I'm letting my experiment collect data, like they do in the CERN, right? And after maybe a month, I have billions of points, and I'm doing maximum likelihood. Am I guaranteed to find the true lambda? And the answer is yes. The answer is yes, and this is why. This is why. This is why, because we can do the following computation. Let's compute the difference. So this is a function of lambda, okay? And I want to claim that when n is going to infinity, the maximum of this function is always given by lambda when lambda is equal to the truth. So let's show this. And it's interesting because it comes from an information theoretic known result. So let me denote the truth of lambda star. And let me compute the difference between this function at lambda star and this function at any other lambda. Now you will see why it's actually convenient to work with the log likelihood instead of working with the likelihood. Okay? So this is 1 over n, sum over all event. Of course, the likelihood is a product of this sample function here, this one. The log of the product is the sum of the log. Okay, and the log of A minus log of B is log of A over B, so it's the log of P of yi given lambda star divided by P of yi given lambda. All right, but now if I let n going to infinity, this is essentially like averaging over all possible observation of y. So this, when n is going to infinity, they should converge to the average value of this quantity over all possible y's. But remember that y's, all the y's are taken from this distribution. Okay, so let me write it here actually. I like to have a large blackboard. So when n is going to infinity, they should converge to the expectation, well, let's write it this way, of a y. So y, the true y is taken from this distribution. The true y are sampled from the distribution where, well, the lambda is the true one, if you want. And here we have log of p of y given lambda star divided by p of y given lambda. And we have seen this quantity already. This is the Kullback-Leiber divergence between two distributions, p of y given lambda truth and p of y given lambda. And the only thing we need to know about the Kullback-Leiber divergences is that it is a positive, non-negative quantity. Right? So this means the following. When n is large, this average log likelihood, if you want, is always maximized when lambda is equal to lambda star. Any over lambda has a lower value. That means that if you have enough data, if you are really a huge amount of data, and you are able to compute its maxima, and if you are not in a crazy situation when you have degenerate maxima and all that, of course you need to assume some regularities, then this method is guaranteed to work. All right? So there are a few more things that we could say about maximum. So this is called, okay, so by the way, this is called the consistency of maximum likelihood. All right, so that's one of the reasons people like it. And even if you don't believe of this derivation, you don't care, this is how I do, and it's guaranteed to work, and people are happy about it. Yes?
Could you please explain again how you went from this summation?
When I went from here to here? So I'm saying that here, what I am doing is computing an average over all the values of y. When n is going to infinity, the empirical average converge to the actual averages. Okay? Now, y is a random variable which is being actually generated from this distribution. So this is why you have this. All right, and of course this is possible because I know how to write the likelihood, and I know this because I'm treating a physical process which I know how to model. It's not always that simple in reality. Okay, so there are other things I could say about maximum likelihood, and yes?
You don't use the definition of maximum.
Well, I kind of do, right? Because this is only saying that this function here has its maxima when lambda is equal to the truth.
Yes.
So that means that if I take his maxima, well, I'm guaranteed to find the truth. So this is saying that it's actually a good idea to take the maxima, because when you have enough data, you know that the maxima of this function is the one that is exactly what you are looking for. Right, this is exactly what this is saying, that when n is large, this thing here is maximized when lambda is equal to lambda truth. So one thing, okay, so I don't want to go too far into this. There are much more interesting results that you can get with maximum likelihood. In fact, when n is large, you can also look what is the distribution of lambda hat. Okay? When n is large, and you can show that this is very close to the truth. Actually, it's actually asymptotically Gaussian. And the variance here, if you want, so let's say And the variance that you get here is 1 over n times I of lambda star. So this is a number which I will tell you how to compute in 5 seconds. This is a number of observation, which I use small n, I think. Yes, I use small n. This is for uniform prior, yes. Yes, otherwise not maximal likelihood, it will be map. As a matter of fact, as long as you're using a prior which is smooth, you will still get the same result, okay? So the only way you can beat maximum likelihood by using I mean, there are good reasons why you want to use a non-uniform prior, but when n is going to infinity, in that kind of setting, it doesn't matter. Now, of course, it matters in reality because you never are working with infinity. I mean, if you are working here and you have 7 points, you might say, look, I really don't care that the method is exact when n is going to infinity. I want to have the best method for n equals 7. And then actually there are better things to do. And in fact, I think the best thing here will be to use a Jeffrey prior, but okay, I don't want to go too much into this. Though actually, I think that there are more lecture about, well, yeah, I don't want to, but I will be happy to discuss it. So yeah, so this is the typical error that you are making. So, you know, for when n is large, you will be very close to the truth. And the error that you are making, the variance is here, is equal to 1 divided by n times the quantity called I. So you see that essentially your precision is 1 over square root of n, which is good. And this thing here is called the Fischer information. The Fischer information is kind of telling you how much information you have in your observation relative to what you are looking for. And it has a very nice simple definition. The Fischer information is essentially very close to that, actually. So I of lambda star is the expectation over all the event of the second derivative of the log likelihood. All right, so that's a crash course in classical statistics. So it's actually a very nice exercise to prove that, or even to compute it, even with rigorous method. And the Fischer information is a fundamental quantity that is extremely important in statistics and information theory. And you can also use it as a prior, and okay, a lot of things could be done. So this is all nice. And basically, you know, I mean, problem solved, right? I mean, if we have enough data, we do maximum likelihood, we are happy, you are happy, everyone is happy, and it's okay. Now, I want to now discuss a situation which is a bit more... sorry, what's wrong? dy. It's the second derivative of log, of course, sorry. Log of p. The derivative of the, okay, so the derivative of the log likelihood is called the score, and the variance of the score is equal to the Fischer information. Okay? So there are a lot of reasons why the Fischer information is a very useful quantity. By the way, so you're asking me about what to use as a prior. One of the best prior in the world is a Jeffrey prior. And the Jeffrey prior is basically saying that you should use the square root of the Fischer information, which has some effect very interesting because it's kind of change the landscape, and you can interpret this as a metric, and there are a lot of interesting things in this direction. Okay? So by the way, using this prior is giving you much better result for n equals 7. All right, so now this is all cute and everything. But the reason why everything is so simple here is because I'm trying to estimate one number by making an infinite amount of observation. This is fine. Okay, but if we do this, we are set in the 19th century or the beginning of the 20th century, certainly not in the 21st century. Now let's move to maybe more modern example. Okay, so this is classical statistics. Now we move to high-dimension statistics, or high-dimensional statistics. Or, you know, big data if you want, or whatever. I don't. So, whenever we hear about big data and high-dimensional statistics, we think, okay, it's easy. We are in this situation, and everything is fine because we are making a huge number of observations. That's not the case. In fact, in modern application, you are trying something much harder. You are trying to learn a lot of numbers by looking to a lot of numbers. Or if you want, you are trying to infer a large number of elements like that by making also a large number of observations. And that means that, well, you have the word large in it, so clearly there is some way, some complex system or statistical physics things that will set up, and it will. And it makes things much more challenging. So let me give you, again, instead of talking about it, let's just try to give an example. All right, so imagine now that you are making an experiment. And I want to motivate the following problem. Okay, imagine that there is a vector x that you want to know, and you have observing a vector y. So we still observe y. Now I change my notation. It's not lambda, it's x. Okay, if you are in statistics, people will call x theta. And in information theory, they will use y and x. So actually, all these guys are just doing the same thing. They just use different notation. It's true. It's confusing at first. For instance, the dimension of this will be d if you are in machine learning, p if you are in statistics, and n if you are in information theory. Right, so I will use my notation. So this is a vector of size m. This is a matrix of size m times n. And this is a vector of times n. All right, so imagine that there is x, and you observe some projection, linear projection of x. Noisy ones, of course, because everything is noisy in life. And knowing y, you try to reconstruct x. So this is not an academic problem. It's actually one of the most important problems of statistics and signal processing. Let me give you two examples. Okay, example A, signal processing. So signal processing, most of the time what you are doing is trying to, there is a signal somewhere, and you want to know the signal, and what you are measuring as Fourier coefficient. Right? Are given the Fourier modes, and then we try to reconstruct the signal. Actually, there's Shannon who told us it's kind of possible. And so this is clearly something you can write this way, because essentially the Fourier transform will be some, one of the elements will be exactly like that, right? Mu x xi f of xi. That will be exactly what the Fourier transform of a function will be for this vector, right? For this mode. Now, you see that if I write a matrix with this matrix element, I can write the Fourier transform like that. Okay, so the Fourier transform, at least the discrete Fourier transform, can be written exactly as a matrix multiplication. So assume that you have measured some Fourier modes. What do you know about X? That is exactly the same as saying, well, there is this Fourier matrix. I know some projection, so maybe not the full matrix. I don't know the n times n transform, maybe m times n. What do I know about X? So reconstructing a signal from its linear projection is typically what you do in signal processing. Well, Fourier is... all right, now there is a problem because... okay, in my analogy, this is f. The Fourier matrix will be n times n.
You don't know the full lane process.
But let's assume that you don't want to measure all possible modes because it's too much work. Probably, I will come back to this in the last lecture. But most of the time, if you have a signal that is not random, you have only few Fourier modes that matters, right? In fact, Shannon tells you that as long as you are sampling beyond the Nyquist frequency, it should be enough. So there are very good reasons not to do the full sampling. Okay, but yes, we can do m equal to n, and that will be the true DCT matrix. All right, so another example, which is more closer to statistics, is what people call the regression problem, which is typically the kind of thing that people do in startup and hedge fund and everything. When you try to learn a model, say for instance you are Facebook, and so how is Facebook making money? I mean, there are probably many ways. One of these ways is they are trying to sell your profile to people who send you advertising, okay? And then people should decide if they send you an advertising to buy an umbrella, which is my case. Yeah. For some reason, I have tons of advertisements for umbrella on Facebook, or they want to sell you expensive watches. And of course, Facebook needs to know essentially how much money, what is your net worth. If you are rich, probably will try to sell you, hey, there is this great new Tesla car, you look like a great guy, buy this car, and if you're like me, they'll say, you have this fantastic umbrella. And, it's, they have this, I don't know. I'd rather buy a Tesla car myself, but I don't have the money indeed. So they are doing a good job. So how do you do this? So of course, some of you probably even wrote how much money you are making because you wrote your job there. Okay, but if you don't do this, you are still writing a lot of information. I mean, they know about your sex, they know about your age, they know about how many friends you have. So maybe you can make a guess with this. So the way it works is you say, fine, let's take all these guys from which we actually know how much money they are making, and let's build the model. Okay? So you have m person, or mu is equal to 1 to m. You know why mu, like net worth for these guys. And then you're trying to build a model that will be linear in all the observations that you have about those guys. Okay? So for instance, now you have y mu, you will say it's product over f mu I xi. Now these are information that you have. For instance, f mu 1 will be the age of person 1. F mu 2, I don't know, number of friends. All right, and these are coefficients that you are looking for. So this matrix here contains what people call descriptors or features in the language of statistics. And let's do this. We have this vector y. It's a product of this matrix times this coefficient. Okay, so these are all the coefficients for person 1. No, these are, sorry, the data for person 1. And the column here, these are the features. So the first column will be the age of person 1, 2, 3, 4, 5, 6, 7, and so forth, right? And here, these are the coefficients. For instance, you might, in your computation, you might learn that it's good to have, I don't know, 0.2 times the age, plus the sex times 3, plus the number of friends divided by 7. I don't know. So it's kind of guesswork, but it's probably not stupid. It's true that if you have enough information here, you probably hope that you will be able to make a good guess. Okay, so there are a lot of things to be said about this problem, and I will come back to it well, later on. So how does it work? Well, first of all, you see that you can be in the situation where m is equal to n. For instance, if you are doing all the Fourier mode, in which case you just have to inverse this. You can be in the situation where m is much smaller than n. For instance, if you have a lot of features, like you know a lot about many people, but you don't know many people, right? For instance, imagine Facebook is doing this. They have access to a lot of data, but maybe 1% of the people have written their net worth. So n is large. They have a lot of descriptors, like the number of pictures, your age, the number of times the picture is blue. I don't know. I mean, you can do whatever you want. But maybe there are only 100 people who are given, from whom they know the age. Or maybe it's the opposite. Maybe they don't have many measurements. Right? Maybe, for instance, you are in medicine and you are doing some trials and you have a huge data set. You know a lot of people, like 1 million. It's never like this in medicine. It's more like 20 when you read papers. But you have 1 million data sample. And for them, you know only the blood pressure, the age, and the sex, and you want to predict if they have a terminal disease or not. Of course, that won't work. So in modern statistics, that's really a situation where you can have every possible variation. N large, M small, M large, N small, the two of them large, but then one could be logarithmically large and the other one exponentially large. Or maybe the two of them are large but the same order, and so on and so forth. And a lot of things can happen there. And what I want to do in the following, and it's basically to tell you that there are a lot of phase transition, and we will map this into the context of statistical physics, and we will see phase transition, first order, second order, all the things that we are used to in thermodynamics. Okay, so let's try to solve this problem, and then we translate it into a statistical physics problem. All right, so let's try to solve it, and we will do exactly the same as we did before. That is to use maximum likelihood. So it's natural to think that you are not observing exactly f times x. In signal processing, you have always noise. And if you are doing this regression model, well, clearly the truth is not like this, right? I mean, it's not true that the amount of money you are making is determined by linear combination of crazy features. So you cannot really, try to invert this directly is a bit crazy. Fine. So maybe what we should do is to say, well, there might be some Gaussian noise here. Right? Okay, yeah, we could be doing this. So in that case, if we do maximum likelihood, well, let's write the likelihood. So P of y given x. Now, well, it's essentially, if this is a Gaussian noise with uncorrelated entries, it's essentially that. Y minus fx. So we observe our y will be basically Gaussian with a mean fx, but there will be some noise here. So the maximum likelihood estimator, again, should be given by the max of the log of that, so the argmax log p of y given x, or if you want, by the argmean of y minus fx. Norm 2. That means that this is essentially the sum of the square of the difference between y and fx. Right, so essentially, if we do maximal likelihood, we say, okay, fair enough, we need to find x such that these two are as close as possible. So this is an easy problem to solve. You know, I mean, this is, after all, y minus fx transpose times y minus fx. And y transpose y plus x transpose f transpose f x minus 2y x transpose fx. And if we take the derivative with respect to x, what we find is that we need the following condition. F transpose f x hat is f transpose equal to y. This is called the normal equation for this problem. This is called also minimizing sum of squared. And again, this is very old. I think Bernoulli was the one who invented this, and it was popularized by Laplace and more importantly by Gauss. All right, so this is nice, but this is not giving us a direct solution. And I want to say a few words about this. So imagine, so by the way, let's look at the sizes. This is n, this is m, f transpose is m is n times m. So this is a vector of type m. F transpose f is n times n, right? So this is really a vector size with n number equal to n number. All right, so naively you might want to say, fine, let's take the inverse of the matrix F transpose F, and then we write is the inverse of this matrix times F transpose Y. Right? This is true. This is true. Except you're not guaranteed that this matrix is invertible. In fact, if you think about it, here you have taken a matrix which is m times n. So the rank of this matrix is m at best, by the way. If all the columns are independent, sorry, if all the columns are independent, yeah, and the line, well, if you have enough independence, the rank of F is m, or n, I mean, actually the minimum of the two. So let's take, for instance, the situation where m is smaller than n. Then F has the ranks m, F transpose F has also a rank m, but then if you try to inverse a matrix with a rank m, well, you know, you will compute the eigenvalues, many of them will be 0, it's not invertible. So this is true only if m is larger than n, and even in that case, you also need some independence, because of course if some of the vectors are the same, and you know, it's really hard to get independence, because for instance, you are saying you are taking the age, let's say that you are measuring the age of someone, and its net worth. I mean, this is pretty much correlated. Usually, the older you get, the more money you are doing. So you think you are measuring many independent quantities, but maybe they are all the same, and so this matrix will be badly conditioned. So this is not always guaranteed. Okay? But still, if m is larger than n, you might be able to do it. Otherwise, otherwise you cannot do this. You can try to do something else. Well, otherwise, what happens? I mean, this is, you know, why is this necessary? Because we are trying to learn n elements from m measurements. So obviously, if we are measuring less information that there are things to learn, we have a problem, right? So that's life. But sometimes this is a situation. Sometimes we don't have enough measurement. So in that case, well, this is a set of linear equations which is under constraint. There are many solutions to it. What to do, which one to pick? Well, it's not clear. And actually, well, it is clear this day, but it's not clear a priori here. One of the things people like to do, for instance, is to do this. F transpose minus 1 times y. So now you see that the matrix I have to invert. So if you don't believe me, take this, plug it here, and you will see it works. So this is one particular solution. It's called NL. No, it's not called NL. No. It's called the least norm solution. Because between all solutions, this is this one which has the least squared norm. Why to choose this one instead of another? Well, no reason. So maybe that will work, maybe that won't. So what we see here is that it's really important to control what is going on between the number of measurements and the number of elements we want to learn. Also, maybe using a flat prior on x and to do maximum likelihood was not the best thing to do, because we don't expect really that all these vectors will be equally probable. In fact, one of the things that has changed a lot statistics in the last 20, 50 years is to say, well, even less, is to say that between all vector x, people try to find are vectors with a lot of zeros. Why is this? Because you are measuring so many things, but probably most of them will not even matter. So you try to express a solution as a combination of a very few number of elements. So there are a lot of things like this which have, been very important into building modern statistics, and we will move on in this direction lecture 2 and 3. But what I want to do now is really to insist on this and to say that there are things going on when m and n has the same order, and in fact here we see that, well, when m is larger than n or smaller than n, we have a drastic change. Or we have an over-constraint problem. At m equal n, we have something which is exactly well behaved, and in the other case, it's under constraint. All right, so let's try to transform this into some kind of statistical physics analogy now. All right, let's come back to our Bayesian formulation. Okay. Now let's try to see what this is. The posterior, okay, as usual, z, p of y, given x, p of x. All right. So I know this guy. Now we'll try to say that maybe for P of x, I should not take a uniform prior. There are a lot of clever things you might want to do. I will do a stupid thing. I will say, well, first of all, probably I don't want x to be infinitely large. I don't want some of these elements to be too large. So probably what I should do is to try to penalize vectors which are too large. Why is this? Because I certainly don't want something in which one element here is infinity and everything else is zero. I want to have things a bit balanced. Okay, so in this case, a natural thing to do is to say, fine, this is 1 over z. Okay, there's some normalization that I forget here. So everything like square root of 2 delta, they are absorbed into S. So, for instance, I might want to do something like this, to put a Gaussian prior on X. Right, this way, all the elements of X, I'm trying to kill, to put a penalty on the value which are too large. So again, squared. Okay, now if you try to maximize the posterior, you will have something which is slightly different from maximum likelihood, because now the prior is taking is kicking in. So maximizing the posterior is called the maximum a posteriori method. So map, maximum a posteriori. If your prior is uniform, map is the same as maximum likelihood. Because of course, if this is a constant, I have to maximize this, so the same. If you have a prior, it's slightly different. Okay, so just a side remark. All right, I will compute the maximum of this in 5 seconds, but first of all, I want to try to convince you that what I have written is really a statistical physics problem. And y mu. Okay, no, how did I do? Let me expand the square again. Okay, this is how it looks. I will drop the arrows, otherwise I'm getting crazy. I have this. Okay, so let's forget about. So if I expand this, I have the y transpose y. But I don't care about y, because this is a distribution about x. So I will just say it's proportional to, and everything which depends on y, I will absorb into the definition. So we have this. Then we have plus y f times x divided by delta minus x transpose x divided by sigma squared. Okay, and so it's again, well. So F transpose F plus 1 over sigma squared divided by delta x plus y f x divided by delta. All right, so the posterior distribution look like that. Now, I'm claiming that this is, and this is kind of obvious from the way I wrote it, it is nothing but a statistical physics problem, right? I mean, this is a partition sum. And this is minus beta h, sorry. Yes? Right, so if I set beta equal to 1, this is just an effective Hamiltonian for a problem. Yes? Well, so let's see what I did. First of all, I don't care about it because I will compute it. at the end, so I might as well I don't care if I compute z tilde tilde or z tilde tilde times square root of 2 or something. But yes, you can, right? I mean, from here to here, I drop the square roots that were in there. From here to here, I think I drop the YY transpose. But the point is, I will have to integrate that, and I will have to compute this anyway, so I might as well absorb the constant and recompute at the end, right? What is important is that since this is probability on X, all the dependent in X is in the Hamiltonian. So, I mean, this is really like a statistical physics problem. I mean, the thing here is like a Boltzmann distribution. And if you want, that's a problem of continuous spins. For instance, you can think about the X as a vector of continuous spins. Well, let's write it. I mean, if the Hamiltonian, for instance, will be minus X transpose J X plus Bx, so that the Hamiltonian, that will be the Hamiltonian of a magnetic system with interaction, a matrix interaction J and an external field B. This is exactly what we have here, right? I mean, we have J, which is equal to F transpose F divided by delta plus the diagonal matrix divided by sigma squared, and B will be Y times F divided by delta. Okay, so it is really like a spin system, and actually a disordered spin system, because the interactions are coming from the data. So we could be trying to solve this with statistical physics problem, and this is what I want to do. Sorry? This is exactly the spherical model. Yes. This is exactly the spherical model. If J will be a constant, that will be the spherical model of ferromagnetism. If J is random, this is the spherical model of spin glasses. Yes, this is a spherical model. Right? So the spherical model is really something that corresponds to that kind of problem. And so, I'm not inventing the connection here. I mean, that's the statistical physics 101 or maybe 102, and that is, sum of linear regression of sum of squared is statistics 101. So it's pretty much connected. All right, so there is a connection. So there are many things that we might want to do here using physics, and we will be discussing the two of them. One is, well, we maybe know some clever way to solve this model. Okay, actually, this one we know to solve it because this is just a Gaussian form, and we know everything about Gaussian integrals, so that's easy. But it's easy because I choose the simplest example. What we will do now is to kind of build up more interesting and more challenging problems. So there are maybe ways that we have in statistical physics to approximate this thing, to compute them, so we can use StatPhys to develop algorithms. Yes? Yes. Yes, yes. Yes, hold that thought for 5 seconds. Yeah, there is. We will see it. 2 minutes. I'm coming to this. So there, one thing we can do is using statistical physics technique to kind of solve this problem and develop new algorithm, and this is cool. One of the things we might want to do is to try to make sense of all these m equal n and everything, and to try to see, in simplest situation, what kind of phase transition we observe, and to try to make sense of this problem. Okay, in that case, we cannot do this with real data, obviously. I mean, otherwise it's too complicated. So one of the things we might want to do is to generate random matrices F, and try to see what is going on here for that kind of problem, when we have generated things according to some random matrices, and try to see what happens when m is larger than n, and so on and so forth. And that's the kind of strategy that I will discuss, and you will see it's actually telling a lot of interesting information about this problem. Okay? So that's the plan. Okay, so two things that I want to say. 15 minutes, that's very good. Okay, so answering your question. All right, so let me try to answer your question. So let's try to take the maximum of the Boltzmann measure. By the way, this is not clear, but this is the best thing to do. Ah, yeah, I didn't say that. What does it mean, map, now? Map is saying you have to, or maximum likelihood. Okay, maximum likelihood was when I maximize this. Map is when I maximize the product. So what does it mean? It means I'm trying to take the most probable x. And that means I should take, if this is exponential minus h, up to some constant, that means I should try to find the lowest possible energy. So finding the map estimate, or the maximum likelihood estimate, if the prior is uniform, is nothing else than trying to find the ground state of the Hamiltonian. Right? So the ground state of the effective Hamiltonian you have written, the x, that minimizes the energy if you want, is the most probable configuration that you are looking for. Well, you will see that this is not what I want to do at the end, but that is equivalent to map. Okay? I want to argue that this is not what you want to do. What you want to do instead is to compute the average value of x, and I will tell you why in 2 seconds. The nice thing about Gaussian measure is that the maximum of a Gaussian is the same as the mean of a Gaussian. So in this case, there is not much difference between the two, right? I mean, a Gaussian is like that. So the mean and the max coincide. So not much different. All right, so as I was saying, in this case, we know to compute this, we know to compute the mean, and we know that because we know the Gaussian identity, and we know to integrate that. We know, at least I know with my notes, so let's try to see if I get it right. I think it's B transpose B divided by 4, well, it's probably 2. It's A minus 1, B. There's probably a 2 here. And then there is a square root of, all right, so this is probably wrong. Let's try to see. That looks good. No, it's probably this. Is that correct? Let's see, this is 1 over delta. This should given 2p delta. Yeah, that's probably, okay, so mutatis mutandis constant that are wrong. This is the Gaussian integral. So we know to compute how to normalize this. We know to compute the partition sum. If we know to compute the partition sum, we can compute the average values and everything. Do you need this? Right, how to compute the average values here? Well, the average values, just the same. I have to divide by z to multiply by x. Again, it's something that we know to do. Okay, or in the same as max, it's it is 1 over A. Well, let's write what it is with these matrices. It's the inverse of that, F transpose F delta plus the diagonal divided by sigma squared times B, if I'm not mistaken, and B is YFX over delta. All right, so now if we try to maximize to find the ground state of S Hamiltonian, which again is the same as computing the average, because that's true for Gaussians. This is what we find now. This is the expectation, and this is also X map. Now you should recognize something very close to what we wrote before, actually. I mean, let me rewrite it slightly. I multiply up and down by delta. Not X here, wait. So first of all, if sigma squared is going to infinity, this is exactly what we wrote here. It's the same. Right, and if sigma squared is going to infinity, this vanishes, so it's normal that we find exactly the same estimator. What is important is now, because of this +1 here, for any finite value of delta divided by sigma squared, this will be invertible. So I don't have anymore the problem of inversion. This is always well defined. Actually, this method is called ridge regression. Ridge regression, at least in statistics, is Tikhonov regression in signal processing. And so at least this is always well defined. If this is a good estimate that we don't know, and for that we will have to look at phase transition and what is going on, and that will be for the next time. Okay? So this is, by the way, one of the ways to solve the spherical model in statistical mechanics, and that means that if you know the properties of this matrix, then you can compute pretty much everything you want here. All right, so now let me wrap up and make a last computation. So you see that any time we have some of these multidimensional learning problem, I mean, not any time, I just give you one example, but after all, it's, how could, it cannot get much more complicated than that. I mean, it's just that functions are a bit different by you just have not have a Gaussian and something more complicated, but that's all. So this is pretty generic. Any learning problem like this, multidimensional like that, can be translated into a problem which is a statistical mechanics problem when you have an Hamiltonian that can be super complex or not super complex. So here it's quadratic, but it can be more involved. And then, well, you might want to compute the partition sum, and you want to compute either the ground state or the average values, and that gives you an estimator about what you are looking for. Okay, so this is the root of the connection between information theory, physics, and statistical inference. Actually, it's more like this. Let me add now the last part of the triangle. So the last thing I want to say is, should we compute the mean of x, or should we compute its max? So of course, here it doesn't matter because it's the same, but it's all, I mean, it's just because it's a Gaussian. It's not always the same. I mean, for most probability distribution, the mean is not the same as the max, which is called the mode in statistics. These are usually different things. So which one is the best? All right? So that's the third thing I want to tell. Yeah, that's good. I need probably 10 minutes for this. All right, so now let's try to see what is the best thing to do. So of course, before it was all clear because we were in this very easy situation where we had one thing that we want to know and billion of experiments, and we showed that map or maximum likelihood was good. But here it's much more involved, right? We have this trade-off, a lot of things to measure, a lot of things that we measure, and so it's not clear where we are, so we have to be a bit more clever. So let's see. What we want to compute is an estimator which is good. Okay? What does it mean it is good? Well, we want, three estimators. Estimators and base optimality. So we want to use something which is good. Yes?
You want your
Speak up, sorry.
You want your estimators to be like such that your mean and the maximum would be at the same place.
Well, I might want to do that, but maybe I don't have the choice because, you know, I mean, this distribution here is given.
And the state of the previous example.
Yeah, I mean, that is true. Okay, we could discuss this, but I can be a bit more straightforward and just switch my brain off and do mathematics, which is what I will do, right? And what I want is to have something in which each element is close to the truth. Right? Again, I denote the truth by star. Or let's call this the mean square error, so MSE, so it's a definition. For the mean square error, and it's essentially, well, the average squared error between each element, between your guess and the truth. Okay? What I really want is to have this to be small. Now, it's hard to guarantee that this is small because I don't know this guy. Of course, if you tell me this one and I'm trying many estimators, I will know which one is the best. But, well, I don't know what is the truth, right? So, okay, so this is where Bayesian theory kicks in. So in Bayesian theory, you will say, okay, it's true that I don't know what is the truth, but I have a prior on the truth, right? So maybe what I want to do is to compute the average value of the mean square error according to what I think it should be. Well, what you think it should be is given by the expectation. So there is this quantity which is called the base risk, which is essentially the average over all x, what you think the truth should be of, okay, and so it's distributed according to the posterior distribution. Of what? Of the mean square error. So your estimator, which is a function of the data, right, this is average error I should make if I believe my Bayesian theory. Right, this is my belief what x should be. So this is average error I should be making for a given estimator. So let's say now I want to find an estimator which is minimizing the base risk. So this is called MMSE for minimal mean square error. Right, how do I do this? Well, I want to, well, I will just try to minimize the risk. Well, I will extremize it. Then you have to check that my extremum is a minima, which it will be. All right, so if I do this, what do I find? Well, let's do the derivative. So I derive with respect to x hat. All right, so this is the Bayesian theory. Y is fixed. These are the observations. If I derive this, I find that it's the x. Okay, and here I have probably a factor 2, but don't care too much about this. I have xi hat minus xi. Right, and if I want this to be 0, this means that what I should do is to use x hat is equal to the mean of each values. Right, so in the spin language, okay, if you want, this is the expectation over the Boltzmann measure of xi, and this is what we call the magnetization in physics, right? The average value of spin I is what we call the magnetization of spin I. And what I just shown you here is that from Bayesian point of view, if you want to minimize the mean square error, what you should do is to take as the best estimation the value of the magnetization of a spin. So you see that it's really, it's really what we do in physics, right? If you define a problem, you have an Hamiltonian, then you have to compute the marginals in the probabilistic language or the magnetization in the physics language, and this is the best estimate you can do. So already you see that if you want to just do statistics, you just take your problem, you do Monte Carlo, and you have the answer. And by the way, this is what Bayesian people do. Mostly they do a Monte Carlo. So I hope I convinced you that there is a one-to-one correspondence. I think it's clear. I want to do a last computation that will take me 2 minutes because Lenka asked me to. This is a notion of error that makes sense only if x is continuous, right? If x is discrete, if you are trying to learn something which is plus or minus 1, like a spin, for instance, or a category, maybe you don't really care to minimize this, but you want to minimize the number of errors you make, right? So for discrete problem, maybe the error is better written as the number of, number of error, and this is really sum over I of delta xi hat and xi star. All right, so you can write the risk again. And it's equal to, well, it's the same. dx p of x given y. This is your belief about what x should be. And then what you want to minimize is 1 minus this. Right? And so if you want to find something that minimizes this, your estimator should be in that case. I'll let you do the computation. Arg max of the integral over, okay, let's write it. P so what you should do is to integrate over all possible value, well, whatever. So, what you should actually do, well, how do I write this? No, okay, no, let me write it in a pedantic way. So you integrate here over all spins except I. Okay? Now, integrating over all spin except I is called marginalization. All right? And you take the maximum of this. Now, if I don't maximize, this is essentially the probability to observe x for its value. Right? So this is argmax of P of xi. So that means I should compute the probability to observe in my model xi. Let's say that xi can take plus or minus 1 values. So I should compute the probability to see it up, the probability to see it down. The magnetization, by the way, is just the difference between the two in the spin problem. And then I should take the maximum one. Okay, and you can check that for a spin system, for Ising spin, this is the same as taking the sign of the magnetization. And I'm done here, so that's good. All right, so this is what I wanted to say. So you see that when you start to think a bit more about what you should do, it's not actually always a good idea to take a map, to take the most probable thing, and it makes sense. I mean, taking the ground state is usually a bad idea in physics because you are neglecting entropy, right? And all what I'm saying here could be summarized in the following situation. Imagine that P of y given the observation is something like that. If you take the max, you are saying, oh, I believe that y is this value. But if something looks like this, you know, the probability that it is taking this value is much smaller than the probability that it comes from this blob. And in high dimension, in very large dimension, we know that entropic effects do matter. I mean, otherwise we would not have invented StatMech. Okay? So this is what it's important to realize that taking the map estimate is not always a good idea. And when we try to formalize what is a good idea instead, Bayesian point of view, we realize that what we have to take is magnetization, or for spin system, the sign of magnetization, or if you have more general things, the argmax of the posterior distribution for one variable. Okay? So this is setting the stage for what is to come. So to summarize, what we're trying to do with Bayesian inference problem, well, what you have to solve is a StatMech problem with an Hamiltonian, with its partition sum, and you have to do the usual thing that we do, that is either you solve the problem rigorously, or you do a simulation, or you do approximation. You try to find the magnetization, and this is giving you the best estimate. In the next lectures, I will be moving into more concrete problems and trying to show you what is going on in real situation, well, real, like more realistic situation. And what I want to advertise is the fact that you observe phase transition between moments when you actually are able to reconstruct something and situation where actually it's not possible to do anything. And it's an information theoretic transition which is very close to the kind of thing that Shannon did himself in 60s, in 68, when he invented the communication theory. All right, I will stop here, and I hope I'm not too late.